Now, in these mobile devices, we will also have requirements for high bandwidth connectivity. One example that we may see in these devices first is the requirement for high bandwidth connectivity between the processor and the memory. So this is one of the areas where we'll see the first integration of 3D stacking. We will be putting the DRAMs on top of the processor. This can be realized using the through silicon via technology, TSV, 3D stacking with TSVs, and microbump technology. Again, a technology that we've been pioneering for more than 10 years, and this technology is becoming baseline in the industry. It's an example of such a stack with 6 memory layers on top of a logic device. Now, one can use this 3D stacking in order to get the higher performance, such as in this example. But of course, the 3D stacking also provides an improved form factor and allows the integration of more components onto a single interposer, such as combining all the RF functionality on an RF interposer, as illustrated in this example. In our devices, we'll also have a continued need for higher density memory. And each of the memory technologies, be it flash, DRAM, or SRAM, they all have some of their major challenges and limitations. So also here, in the next couple of years, we will need a lot of new innovation. But there are several emerging memory technologies that are available. And so our view is that RAM, resistive RAM, is one of the most likely successor for the flash technology. That STT-RAM is one of the most likely successors for replacing the DRAM ultimately. But because of its performance, STT-RAM could also be used as an embedded memory to replace a large fraction of the SRAM. So those are some of the technology trends as we see them in these kind of devices. Similarly, for the high mobility, for the high performance devices that are needed in the data centers and servers, similar type of technologies will be needed. But that will be the first area where the optical interconnects may be used because there we will have the most stringent requirements on interconnecting those devices. Now, the 3D technology, which I just explained, using the silicon interposer technology, can also provide a perfect platform to indeed integrate silicon photonics. With these silicon photonics technologies, we can indeed realize these modulators, the multiplexers, the fiber connectors, the demultiplexers, the germanium detectors, germanium on silicon, germanium detectors that will allow us to transform the electrical signals, the optical signals again, into electrical signals. So those are some of the key technologies that will enable these devices for the servers. For the smart sensors, again, similar technology will be used, but here a very important key requirement will be the ultra-low power performance. In order to make those sensors smart, we will also have integrated DSPs on those sensor substrates, and in order to indeed realize this ultra-low power performance that will allow long-term operation, we indeed are using technologies and designing circuits at the near VT or sub-VT operation. On those sensors, we will also have the heart of the sensor, for which a lot of technology innovation is also required. Some of them are like motion-based sensors, accelerometers, gyroscopes requiring MEMS technology, but other sensors in order to measure biopotential, temperature, skin conductance, sweat sensors will be integrated in those devices. Specific for this kind of application will be the need to integrate those devices on flexible and stretchable substrates so that we can integrate them in a patch, a held patch, which is comfortable to wear. This will also allow the integration of the antenna structure on such a flexible system that will provide the low power, ultra low power wireless connectivity to our smartphones. So these are some of the technology trends as we see them. And for each of those applications, we believe there is a tremendous need for innovation, which will be required on one hand on the materials level. A lot of new materials will be integrated. We will see a lot of 3D devices, 3D stacking, but key in all of this will also be a tremendous drive and push to go to smaller dimensions enabled by lithography in order to keep the cost of these new devices under control. It is clear that all of this goes at a speed which we've never seen before, so the challenges are tremendous, but as I illustrated in the start of my talk, the opportunities are also unprecedented. But it's clear that in order to keep up with that pace, we really have to think carefully on how we can bring innovation, and therefore new innovation models have to be considered. We believe that the old innovation model, where a lot of the pioneering work was done like 30 years ago in our industry into these huge corporate R&D organizations, that model really is under tremendous pressure. These huge R&D organizations, think of Bell Labs, some of the corporate Japanese organizations, Philips NatLab in Europe. I think this fully captive model where you have huge R&D organizations in a big corporate organization really is under a lot of pressure because it becomes really unaffordable even for the biggest companies to maintain such huge R&D teams. But at the same time, it really may not be the most effective model because we really have to bring together competences from so many areas. Think about all these future applications in the biomedical space. We have to bring medical competences with electronics competences, with engineering, and it's very hard to do all of that in these captive models. If we look at the R&D scheme, then what we're seeing is if we focus on the development, getting those technologies ready for manufacturing, it's clear that the cost is extremely high. Think about an UV scanner costing like 100 million euro. So even for development, this is very expensive. Also because the development needs to be done on equipment that will be used in manufacturing. It's a very competitive domain. It's therefore moving very close to manufacturing. We've had a period where some of this development was done in a partnership mode, where there were development joint alliances. But I think this model is coming under quite some pressure because most of the leading companies, they are moving their development very close to manufacturing. In fact, nearly all of the top companies in our sector are doing their development in a fab, in a development fab, which is either attached to their manufacturing facility or is part of the manufacturing facility, which is then being extended into a larger area once they ramp up the manufacturing. All of the top companies are doing it in this way because they can reuse the equipment that is used to develop those technologies. And it's also the fastest way to bring development results into manufacturing. Now, also for research, there is a tremendous challenge. The cost is also increasing there tremendously. The point here is also, as I mentioned before, we really need to bring together the full ecosystem. We have to bring together multiple expertises. We have to do a lot of innovation on the materials side. So we have to bring in the materials suppliers, the equipment suppliers, but also at the other end, the fabless and end-user companies. Now, the good thing about the research is that it is more pre-competitive. So we can indeed share this more effectively over multiple partners. So it's clear that these days the development is being done in a captive mode, very close to manufacturing, whereas the research is done in an open mode. And I think at IMEC we have been really pioneering this model over the last 28 years. We've been fine-tuning this new model of innovation, which has become an open a model of open innovation, certainly for the generic pre-competitive R&D. And we've been implementing this model of innovation very effectively along the value chain by bringing together all the key companies, all the leading companies, from the suppliers up to the end users, but also implementing this model of open innovation along the innovation chain. We're working with more than 200 universities and with more than several hundreds of industry companies. And essentially in all of this is also that we have to look at this in a global scale. If you want to do top-notch R&D and innovation, you have to work with the leaders wherever they are in the world. And we should not focus on this in a too regional concept. And we're working in that concept with all the top companies in the US and in Europe and in Asia. These are some of the companies that are committed to our model of open innovation. This includes basically all of the leaders in this industry, the memory IDMs, all of the IDMs, the logic, Intel as a major logic company, the foundries, the three major foundries, TSMC, Samsung, and Global Foundries, and also including all of the top fabless and fab-lite companies. Based on a very large network of suppliers and also many of the end system users. In this way, we really bring together a full ecosystem, and in order to drive the innovation in the examples which I showed, it is really important to have all these expertises together. This, by far, represents the world's largest industry commitment to semiconductor research in partnership, and those companies are really providing the majority of our budget, which is close to $450 million per year. We would like to use this kind of ecosystem also in order to collaborate effectively with the industry and the research community here in India, and that is why we have set up, like a year ago, IMEC India, in order to really reach out and use this ecosystem that we have developed over the last 20 years in the advantage also to contribute to developing the industry and the R&D activities here in India. Thank you very much.
Keynote address, I would request Mr. Vivek Sharma to kindly come over and present a memento to our esteemed speaker. The power of the new innovation model, ladies and gentlemen. Thank you very much, Mr. Dr. Luc van den Hove.